Okay, and we'll start the last talk of today. So we have Sepehr Assadi, who's faculty in computer science at the University of Waterloo. So Sepehr is quite broad within CS theory. So I know him from working together on econ CS problems. He also does communication complexity in forms of lower bounds and different kinds of algorithms. It looks like today he's talking about streaming algorithms. So thanks for being here.
All right, thank you. Thank you everyone for being here, and thanks for the organizers for inviting me. Congratulations. So today I want to talk about this optimal streaming lower bounds for maximal independent set. For that, let me say, these people here today talked about the econ CS part of Mark's contribution. I learned a lot from him for his work on like this new lens of looking at communication complexity through information complexity. It's been very helpful, and I think I picked this talk partly because I can talk a bit about that. Also partly because I mentioned this problem to him in 2018, I think, first time I met him, that this is a question I like to one day solve, and like 6 years or something later, we know the answer. So I wanted to report back. All right. And this is joint work with Christian Conrad and Kiran Naidu in University of Bristol, and my PhD student, John Sundarsan, which is here actually also. All right, let's start. So I'm going to go over two backgrounds, one on the model. Let me just define the model. We are going to work in the streaming model. It's been originated in a series of papers in 70s and 80s on various problems with different lenses. And then I think it was formalized in these two works, or primarily a streaming model was formalized in this work of Alan Matthias and Szegedy in 96. And then later for graph problems, which is the topic of this talk, Feigenbaum et al. Like formalized it specifically for the version of the problem we want to look at. And one way to talk about it is this model. Let's say I have a graph G. It has vertices 1 to n. I know the vertices. They're really numbers 1 to n. And there's some unknown edges that are coming in some arbitrary order and are given to me. And I want to process this stream using a limited memory of my algorithm. And then at the end of the stream, output the answer to some problem. And I have an n vertex graph. So if I allow myself a memory of roughly order n square, then the problem from a streaming aspect becomes trivial. I can just store the entire stream. So then that streaming aspect is irrelevant. That's now bounded space computation. But what if my space is a lot less than n square? Okay. And it turns out that Feigenbaum et al. Said, like, observe that perhaps the sweetest spot for solving graph problems is to allow yourself a space proportional to number of vertices. There's some nice trade-off happens here. Below that space, most problems that you care about are completely intractable. When you allow more space, then you can start saying something meaningful algorithmically. Okay, so this is the regime we are focusing on. They also said that let's allow ourselves a few passes over this stream. Okay. And if it doesn't sound natural to look at a stream with multiple passes, you can think about it as this model, for instance, that your data is sitting in your hard disk. In a hard disk, it's not easy to, like if you pick a off-the-shelf algorithm and run it on a data which is sitting in your hard disk, it's going to take forever because it will make random access to your data. Okay. But a streaming algorithm actually reads its hard disk in a sequential manner. So think of your hard disk as being your stream, read it in a sequential manner, and use your memory or RAM of your computer as the memory of the streaming algorithm. And it turns out actually that semi-streaming algorithms now people have implemented them. And in multiple cases, at least I know that they're giving the fastest algorithm we know when you want to run things on your laptop, on your hard disk for graph problems. So if people are very interested, I'm happy to talk about those at the end of the talk or later. But for me, really, today, I want to just focus on the model. Let me just tell you what do I mean by an algorithm here. And I want to define it in a very simple, let's say, combinatorial way. Just work with this definition. Okay. So an algorithm here for me is just the following. It's a very restricted family of a branching program. Let's look at this graph. It has, let's say, W vertices in each layer. All the edges go from one layer to the next layer. Every vertex has out degree of n choose 2, n being the number of vertices of the graph. Okay. So the way so an algorithm really is this graph. Okay, at the bottom. And if I want to And the outigre, as I said, is n choose 2. So how does computation using this algorithm look like? Well, you read the first edge of your graph. Okay, so you have a graph with m edges. You put it in those slots in some arbitrary order. You start from node 1. The edges of this graph are labeled, this bottom graph are labeled with n choose 2, all possible pairs of vertices. Okay, so you read E1. It tells you that the first edge is from U to V. Okay. There is an edge incident on 1, which is labeled by UV. You just take that edge to go to this state of the memory, or to this state. Then you read the next edge that is written there. It is another pair of U choose, like UV pairs, which corresponds to one of the edges going out of this vertex. I've not drawn all the edges. This graph at the bottom, every vertex has n choose 2 outgoing edges. So you start from here, you read that edge, you update your memory state to come here. You read the next edge based on its content, you update your memory state to come here. You continue like this. At the end of the first pass, you end up at some vertex. Okay. So really, I can write an algorithm as this graph at the bottom. This is all that an algorithm is to me in this talk. And if I have multiple passes, I have 2 steps. Of like if I have a 2-pass algorithm, I'll do 1 round of these steps, then the last states of the previous graph, the last vertices of the graph of the first pass are the first vertices of the graph of the second pass. They don't need to be the same graph. Okay, so what my algorithm does in its first pass can be very different than what it does in its second pass. But the order of edges that it reads are the same. And then I do this thing for p passes over my data. At the end, the final vertices that I have at the very last level, instead of having outgoing edges, have answer to my problem. Okay, so each of them has a potential solution to the problem. If it's a decision problem, some of them is labeled 0, some of them are labeled 1. If it's a search problem, let's say you are finding a spanning tree, you've written a certain spanning tree in those states. Okay. So is the model clear? This is all I mean by computation in this model. In terms of parameter, the number of vertices here, this width is 2 to the s, where s is this O tilde and the memory I allowed myself. Because if you think about it, an algorithm that has O tilde and memory, it's going to have 2 to the O tilde and different possible memory states. So I capture that by the vertices in the layer. And the length is basically p times m. M is the number of edges, p is the number of passes of the algorithm. Okay. So we want to understand how does these graphs or these branching programs at the bottom can solve certain problems. And we define what we mean by computation. Good. And if you're curious about what does randomization look like in this model or for this branching program, actually we are going to be very relaxed with that definition also. Instead of, when you want to design a randomized algorithm, instead of designing one branching programs, you design a distribution over different branching programs. At the beginning, you just sample a branching program independent of your input from that distribution. Okay, and then you run that particular branching program for this input. Okay, so it somehow means that I'm not even charging my algorithm for storing its random bits and things like that. I want to just mention that there's a very long history of studying these branching programs. They're one of the best tools we have to study time and space trade-offs for algorithms. I was looking at a very restricted family of branching programs. You can define them a lot more generally. Okay. So now instead of time and space trade-off, in this talk, we are looking at them to prove pass space trade-off. How many passes do I need for like this particular space regime that I have for solving a certain problem? So is the model of computation okay? All right. So that was the model. Let's talk about the problem. The problem I want to talk about is maximal independence set. So if I have an undirected graph like this, as an independent set is a set of vertices that don't have any edges to each other. So these blue vertices form an independent set. Maximality means that I cannot greedily extend this independent set. This independent set is not a proper subset of any other independent set. Okay, this is not maximum. Finding a maximal independent set is an easy task, really. You can just greedily pick one. So this is the problem I want to study, finding a maximal independent set. And the motivating question we have is that how many passes are needed by these semi-streaming algorithms or these particular restricted branching programs that use O tilde on a space before they can find any arbitrary maximal independence set in your graph. Okay? I don't have a slides. I was not even planning to talk about the motivation of why we want to solve such a problem. It's interesting. I'm going to tell you more about what we know about this problem. So people have studied maximal independence set in the 80s through the lens of parallel algorithms. That's one of the most famous algorithms here is Luby's algorithm in the like in NC2, for instance, or in parallel algorithms. You can just take that algorithm and almost verbatim implement it in a streaming, and it will give you an order log n pass algorithm. Okay. So we know from classical parallel algorithms, we can solve this problem using order log n pass in the streaming mode. Then the main interesting result is by On, Cormod, Goa, McGregor, and Vert that show that actually you can exponentially improve over this. Okay, now that you have this more powerful or this different semi-streaming model, you can actually get an exponential improvement over this classical parallelism bounds. Okay, and this was important. So like maybe you've heard of, okay, PRAMs may not be that relevant when you're working with actual computers. Then they were saying that in a streaming or in some other, for instance, massively parallel computation models, you can actually compress down the number of rounds that you need in classical parallelism from log n exponentially down to log n. The techniques here turn out to be super useful for solving various other problems, matching, vertex cover, correlation, clustering. That's perhaps the reason, that is why I was very interested in maximal independence set. It's a very good test bed for studying various algorithmic techniques. Good. So that was algorithmic. So we know how to solve this problem now for almost over 10 years in log n passes. What about fewer passes? Can I solve it in one pass, for instance? And for problems very similar to maximal independence, we know how to solve them in a single pass. Two examples, one is maximal matching. Maximal matching is a straightforward to solve in a single pass. Leave that as an exercise. You can just greedily maintain it. Okay. Delta plus one coloring of graphs with maximum degree delta. Again, you can do in a single pass. This one is not as straightforward, but you can do it. Okay. And the nice thing is that these problems in a classical setting, the sequential or classical algorithm that you write for them looks almost identical for all three of them. Okay. But we knew we can do this thing in a single pass for these two problems. What about MIS? We knew that you cannot do this thing for MIS already back then, 5-6 years ago. We could prove that if you want to solve MIS in a single pass, you need omega n a square space. Okay, so the best thing you can do is to just store the entire graph. Okay. Now the question is this gap of, okay, I know I need more than one pass, and I know I can do it in log n passes. What is happening in the middle? And this is the question we want to answer. And at this point, is there any quick question I can answer? No. So good question. No, even two. Probably two is like one is qualitatively different than the rest. Like usually when you can prove two pass lower bounds, then you can start going after. One reason is that the moment you have two passes, you're seeing your input more than once. It correlates all your memory states with the input. One pass, sometimes you can do these tricks that you cannot. So we didn't know anything more than one pass. That's true. In which direction? Finding a maximal independent set of claw-free graphs, for instance. I don't know the answer to that, actually. I don't know the answer. I'll think about it. If I had something, I'll let you know. Just one thing is that there are these families of graphs called bounded neighborhood, like the neighborhood independent, like every vertex has a small independent set in its neighborhood. those graphs, we know how we can compute maximal independence set. But that's the only specific family of graphs I know. One more comment here. You want to look at the families of graphs that can also be dense. Like, for instance, it's not a good question to ask, can you solve it on planar graphs? Yes, because you can store the answer. All right, so now let's talk about the result. So our result turned out, we can prove that actually this log n passes that the algorithm gets is asymptotically optimal. Any randomized algorithm for finding a maximal independence set also requires log n passes. And so this is asymptotically optimal. In fact, it's quite sharp. I think we can get like half times log n passes, where the upper bound is log n passes. Okay. And in light of this algorithm of Ahn et al. That I said, this is optimal. And the interesting thing here was that this was really the first time we could prove optimal multipath semi-streaming lower bounds for any natural problem. Since then, now we have a couple of other lower bounds for matchings in dynamic streams or for minimum spanning trees, but there's still, these are very few instances that we have optimal lower bounds. O tilde n. O tilde of n. Yes. So by semi-streaming, I always mean O tilde of n. Good. So it is this. Let me just write it here. Sorry for the audience on Zoom. But p passes n to the 1 plus 1 over 2 to the p. This is a small off one. So if you have p passes, you need this much of space. Okay. Yes, W is exponential. Yes, exactly. 2 to the power p. Yes. So once you do log n, this starts becoming n, and it is no longer interesting. Okay. Below log n, this is larger than n poly log n. Okay. Yeah, so this is almost tight, like modulo some +1 -1 here. We have an algorithm that matches this. Yeah. In fact, the lower bound somehow follows the algorithm trade-off and the idea. I'll try to say something about that at the end. So the technique that went behind this lower bound was something we called hierarchical embedding. That's what I would like to talk about the rest of the talk. It turned out to be useful for proving these type of lower bounds for other problems. More recently, kind of not directly, but its ideas were helpful to even prove distributed lower bound in this congest model for like this problem called triangle detection, for instance. And should say that like if I want to be very precise, it's better to state these results in the language of communication complexity. Okay. But I don't want to define one other model in this talk, so I'm just going to try to do everything in the streaming language. But the way they're proven, they're first proven with like multi-party communication complexity, and now we can prove them even using two-party communication complexity. Okay, so there are two almost disjoint parts that go, at least technically, two disjoint part goes into proving this result. There's a combinatorial part. We want to create some family of graphs that are looking very hard for our algorithms. And for lack of better words, let's just call them magical graphs here. If someone have a suggestion for better word at the end of the talk, I would love to hear it. And then you want to analyze those hard instances that you create using some information theoretic argument. In particular, the main tool is something called a round or pass elimination. And then you'll combine these things using some, let's say, some technique that combine them. You do some gadget reduction. These two will form some very strong building blocks for you. Then the rest, combining them, is more like a usual thing of combining some gadgets with each other to prove the lower bound. Now, whenever I want to talk about these two, I'll have this. It's hard to decide which of the two of these to talk. So this time, to not make a decision, I try to talk about both of them at the risk of backfiring and not being able to talk about either of them. Well, so let's start with the information theoretic part. And if it didn't finish in time, I won't talk about the other. Okay, so this is, so let's do a quick background or reminder. This is very cool technique in communication complexity called round elimination. It goes back to the work of Milterson, Nissan, Safran, Wigderson in the 90s. And it has an analog in a streaming called pass elimination. And let me tell you how it looks like. The idea is how to prove a lower bound for P+1 pass algorithms using an already existing lower bound for P pass algorithms. So the idea is this. Suppose I have some problem F that takes a stream sigma chosen from some distribution mu, and the problem is defined for P passes over this particular stream. Okay, so this problem I have. Now let me define a new problem based on this. So I will pick k different streams from the independently from this distribution mu that I had. So I had a distribution mu which was hard for P passes. Now I'm defining a new problem. I'll say that pick k different streams from that distribution and append them right after another. Then at the end of your stream, also add this integer I. Okay. In practice, when you want to use this to prove a lower bound, this I is a gadget that does something. For now, just think of it as a number. I just put this number at the end of my stream. Okay. So now I have this larger stream. So this is now my new stream sigma. And on this stream, I want to define a new problem. The problem G that I define over this long stream is this problem that look at what was I, come back and figure out the ith stream you put here, and solve F over that ith stream. Make sense? So I had a problem F that took one of these things as its input. I'll put K of this, added an index I, and define my big problem, problem G, to solve this. I points to one of these, and I ask it to solve this problem in F. And then if I define the space complexity of a problem in P passes to be the space you need to solve it using a streaming algorithm in P pass, what want these round elimination or pass elimination arguments prove is that if you want, look at this problem G, in P+1 passes, the space you need is minimum of K, or the space you need to solve F in P passes. Let me try to interpret this. Suppose you have a streaming algorithm that makes one pass over this part of the input, okay? And its memory is less than K. Then this algorithm probably have stored less than even 1 bit about a random instance or a stream here. So that algorithm has a very small knowledge of memory of what has happened in the past, okay? Now here I give it, oh, I want to know the answer on the ith coordinate. It only learned it at this point. But at this point, I've effectively remembered nothing, okay? So now I only have P passes. I can go back, ignore everything and solve the problem here, but I now only have P passes. So if I use less than K a space, I have to pay a space proportional to a P pass algorithm. And this is good because I went from a P pass lower bound to a P+1. Everything is good. This is what pass elimination or round elimination will look like. Let's try to use this to prove a lower bound for any graph problem. Okay, I want to prove a lower bound for a graph problem that the lower bound is stronger than number of vertices. Okay, so roughly what does this want me? First, I'm proving an omega n lower bound, so both of these quantities have to be larger than it. Okay. The first quantity tells me that I need to put at least larger than n many subgraphs inside my input. So this big graph that I have, it should have at least larger than n many subgraphs that are defining the problem. But this quantity can never be larger than the number of edges. I can always store my input. Okay? So it also tells me that each of these subgraphs have to have more than n edges. So what I want, if I want to use this lower bound, I have to create a graph that has more than n many edge disjoint subgraph, each with more than n many edges. Make sense? So I need a graph that has more than n edge disjoint subgraphs with more than n edges. Okay? And that's turned out to be not possible. No, a graph can only have n choose 2 edges. Okay. Even if you do this thing as a multi-graph, this is still not possible because the argument was actually pair of vertices. So yeah, you can't do this technique. Good. So let's change this a bit and let's do something slightly different that turns out to be good enough. So again, I want to create a hard lower bound from a p-pass problem, which is f. I want to create a new lower bound for a new problem. This time, instead of putting k instances of those problem, I pick a matrix of input to the problem f. Pick these r times t different streams, and I just, again, append them all next to each other. And then, again, I'll put an index I. But this I now points to a column of this matrix. Okay. So this big thing is now my stream for the new problem. And this I now points to a column of this stream, which is collection of multiple subproblems. Okay. And in the new problem that I'm asking you to solve, instead of solving the problem for one of them, I want you to solve it for every single one of these instances. Okay, so the new problem that I have is not a Boolean problem. It's like this makes more sense for a search problem. Okay, you had a p-pass lower bound, create this matrix out of it as input. I will tell you solve the problem on the ith column. Okay, so you have to output r different answers. Okay, this is just a small change we make to define problem h. What we can prove for this new problem is that actually you either, again, store at least one bit for each of these sub-instances, so r times t. If you are not storing that, you have to solve r independent problem in the next pass. Okay, so your problem becomes r times harder. You know, the important thing is that now instead of having SC, I have an r times SC. Good. The same argument that, okay, if I didn't remember r times t bits by the end, I've not remembered enough number of bits about each special instance. So for each one of them, I need to spend a C of p passes, a space, okay? And now that I have to solve r of them, maybe my space become r times large. Is the intuition okay? Does anyone see a problem with this? We have to prove that. There is the part that we have to prove that, but as I stated, this is like bad. This doesn't work. Okay. I've been cheating a bit. That the problem is that if I put these streams one after another, a space has this reusability thing. No, I can solving r sequential instances of a problem does not become r times harder in terms of a space. You just solve one of them, store the answer, you solve the next one, store the answer, and you move on. Okay? So in fact, if you want to prove this thing, the stream you have should not look like this. You should start chopping off the streams into multiple parts that these two together will form the first stream. Okay? This part and this part together will be the input to the first problem. Okay? This way, when your streaming algorithm goes over these things, have to remember something for this subproblem and then something for this subproblem and so on and so forth. And if you do that and you massage things enough, you will be able to prove this. This is the part that is tools that Mark has been spearheading using information complexity become very helpful to prove some direct sum result. That now that I'm solving r parallel problems, it becomes really r times harder as well. But you can prove this. Good. So now, does this new bound, does it make it better for graphs or not? So this was classical round elimination. It gives you something, a formula like this. And if we wanted to apply it to a graph, we needed a graph with more than n many subgraphs with more than n edges. So those graphs don't exist. In this new version, what do I need? I have a bound that looks like this thing. Okay. So for instance, let me show you some setting of parameters. What if r is roughly n, t is root n, and each of my subgraph has root n edges also? Okay. Then r times t is n root n. Good. R times SC in the ideal world that you need to spend a space proportional to number of edges is n times root n, n root n. Good. What is this thing? This is saying that I need a graph with n root n subgraphs, each with root n edges. That's not out of picture. No, there are graphs. Okay. So at least on the surface, the very naive argument of counting the number of edges and saying, oh, this doesn't work is not problematic here. Okay, good. And just the sense that I will not go through why we get a trade-off like this, but if you see a bound like this, basically in the first pass, we prove n squared. In the second pass, we prove n root n. Third pass, we prove n times 1 plus 1 over 4. Each time you're getting a root on the extra term you have. That's give you those trade-offs.
What's special about the n in this context? Memory? Is it very easy to prove low bound below n?
Yes. In summary, the maximal independence that your output is so large, you cannot even do anything below n, like the way I was defining it. But even for many decision problems, the graph connect, most of the problems below n, things become very different. We don't know that. And in fact, I highly believe these things are, like the statement is false for random order. I think in random order, you should be able to get much better than log n. Thought about this, we don't even know lower bound for a single pass. And I think you should be able to solve it in a single pass. This problem is very different when you have random order access. Okay, so I talked about some edges and distance like this, but this is just saying that in principle, this is possible. Just having edge disjoint graph is not at all enough to be able to implement this strategy. So the second part of these techniques and this work is to create a graph that allows you to use some communication bound or some space, some trade-off like this, and put this inside a single graph. So let me spend the rest of the talk telling you roughly about how such graphs should look like. And if you did not follow the previous part, or you can completely ignore what has happened, this part is different now. Now that we are talking about a graph theory question, kind of the question is like this. I want to put many groups of graphs into a single graph without creating interference between them. And I will define this thing in a formal graph theoretic sense. So just a quick reminder that my goal is to prove a lower bound for MIS. So I want to somehow say that solving an MIS on, think of each of these as being a graph. Solving an MIS on a graph consists of all of these things plus some gadget requires me to solving MIS on R subgraphs chosen in one column. Okay, this is what I want to get, which kind of looks like I have to take my graphs, these are small graphs, and put them inside a bigger graph, such that to finding an MIS of these big graphs, I should find MIS of one of these columns, one specific columns that the algorithm, like the adversary chooses. Okay. Like this is a bad shape for drawing the graph. This is not good because I should not put those graphs all separate from each other. Like this, that will make my graphs look very sparse, this big graph. I have to just pack all of them on top of each other. Okay. So let's just start with an exercise. How does these magical graphs look like? Suppose I have some target graph in mind. Okay. For us, these target graphs are p-pass lower bound graphs. Okay, so they have a specific structure. But for now, let's look at a very simpler graph. Let's say triangle. Let's say I have a triangle in mind. Okay. I want to create the following graph. I want to pick R times T copies of a triangle and put them inside a graph G with the following property. In this example, my R is 2 and T is 3. These R times T copies for T groups, each group has R triangles inside them. Okay, so I have 3 groups here with different colors. I have this group of 2 triangles in red, this group of 2 triangles in blue, and this group of 2 triangles in green. So I want my graph to have these groups. What is the property of the groups? If I look at one particular group, let's look at this one. It consists of 2 triangles. They are disjoint from each other. And most importantly, on this part of the graph, there's no other edges. Okay. So I want to be able to put, let's say, 3 groups, each consists of 2 triangles. And when you look at the vertices of each group, you only see those triangles. You don't see any other edges. This is a weird looking graph. Like, to give you a sense, the first time I wanted to create a figure slightly larger than this to put it in the paper, I had to write a computer program to figure out how to create, because it was hard to create the graph that satisfies these things. But okay, this is on a very simple example, you can create it. So this is one, and this is another. And again, what is the restriction? The vertices that you have, you put this triangle here, but you have to make sure there are no other edges between them. Okay, this is what I want from these graphs. And then after you do all of these things, you actually need them for very large parameters. You want your R and T to roughly look N over B, B being the number of vertices. Okay, because these graphs are going to have roughly B square edges, like in principle. You cannot hope for anything better than this. Okay, these tell you I need to have N square over B square subgraph, each with B square edges. Okay, so I cannot hope for something better than this, but I have to get close to this up to this fact. There is some animation telling you that actually, if you can do this thing, this is not that much lying here. Let me skip that. Let's just talk about, again, how does these graphs look like? So I talked to you about triangles. For our purpose, we need something a lot more complicated. But let's make it even easier. Instead of a triangle, let me ask that I just want to have a single edge. I want to create a graph where these target graphs are a single edge only. Okay, let's look at how does that graph look like. So I want to put a graph with R times T edges. Each of these R times T edges are partitioned into T groups of R edges. Each of the R edges is a vertex disjoint union of R edges. A vertex disjoint union of edges is a match. Okay, so I want my graph to partition into T different matchings. And also, I want vertices of these matchings to not have any other edges between them. So I want them to be an induced match. Okay? So I want to create a graph that has roughly N different induced matchings of size roughly N. Okay? To just see that why that's a weird object, when you add an induced matching of size N, you remove N square possibilities of other edges. You add N edges, and then you say that, look, all these other edges that could have been here are no longer allowed. So you add N edges to your graph, and then you remove possibly N square edges, roughly. But you still want to be able to do this thing omega N time. So on the surface, it looks like you definitely should not be able to do this. But these graphs exist, and this is what Rosa and Zameridi created in '78. On this very particular instance, this is really a Rosa's Zameridi graphs. Okay, if you heard them, they're really interesting graphs. They've been used a lot for, I guess, in like proving some things in number theory, and now a lot in streaming algorithms, in PCPs, hardness of approximation, communication complexity, etc. So on the absolute base case of the graphs we want to create are these magical Rosa's Zameridi graphs. For us, we need to generalize these graphs such that instead of having induced matchings, they have induced copies of somewhat arbitrary subgraphs. Okay, so abstractly think of, you take a Rosa's Zameridi graph and you change each edge with an instance that is hard for a p-pass MIS problem. Okay. I should put a stop here. You cannot change a RS graph, each of its edges with an arbitrary subgraph. There is, for instance, a simple argument that if I wanted each of these target copies to be a clique, you will not get the bounds I was talking about. Okay, you cannot pack so many things inside. So this graph edge should have at least some properties. And it turns out that for us, the only specific property we need is that we need this graph to have a small chromatic number. Okay. As long as we can maintain the fact that the graph we are trying to embed inside this P graph have a small chromatic number, we can do this. And this is going to give us the final construction. If you give me any k colorable graph on B vertices, okay, we can create another k colorable graph G that contains these R times T copies of this graph with inducedness properties, etc. for these parameters R and T, n divided by B, the target I wanted. And I lose this factor, a factor in k and some 2 to the root log k times root log. Yes. So Rosa-Zamerdi graphs, you can make them bipartite, okay? And if you can see our construction also, if you start with a k-colorable graph as a subgraph, we do not blow it up at all. Okay. The only time the blow up happens is that when we go through that reduction to the streaming algorithm, we have to add a gadget at the end that will double the chromatic number. So we start with a graph which is 2 colorable and prove a 1-pass lower bound. Then it become 4 colorable for 2-pass, then 8 colorable. But that loses some 2 to the k factor. K is like log n. We don't lose too much through that. Yes. And for us, we want to maintain k to be n to the small of 1. So all the loss we have here is n to the small of 1. Also, I'm not claiming that these bounds are optimal. Okay. You need some dependence on k. Okay. In fact, n over b times k is optimal when k is equal to b. Okay. But I don't know about this. We don't understand this even for Rosa-Zamerdi graphs. All right. And the final thing, one word about the proof. You start with these 3 AP free sets, these Barron's constructions in number theory. And then people have used them already to create RS graph. The RS graph construction comes from Barron's construction. And then Alon and Abod and Bodwin use these things. Instead of creating RS graph, they create things that have induced longer paths, K paths. And for that, you use KAP free sets. Then we are using constructions similar to those and a graph product that take these long paths and replace it with a k colorable graph. Once you set things up correctly, it uses complicated tools, but once, I mean, the proof is short actually, it's not a long proof. And once you know those tools, creating this graph is not too hard. Good. So we do this thing, you pack these things together. And this allows you to prove some information theoretic lower bound that says if you can pack these many graphs inside a graph, you can get your lower bound. And this is telling you how to pack them together. Then you need some wrapper around this. The wrapper that goes around this really is business as usual. It's like a gadget reduction. Once you have these 2 tools, then you do some gadget reduction to get the final lower bound. And that allows us to prove that, for instance, for this semi-streaming MIS, a streaming algorithm that use OT law in a space, need log n passes. Let me conclude. So there was a time that we didn't have that many multi-pass streaming lower bounds, especially in semi-streaming lower bounds for graph problems. And that has changed. Now we can prove lots and lots of different lower bounds. I had a survey on some of these in 23. It's really outdated by now. So because like by then we didn't know how to get optimal lower bounds. Now there are multiple results that can get optimal lower bounds for semi-streaming. It's this work of Dorr and others, which unfortunately I forgot their name, that prove lower bounds for Maxcot. It's not in the semi-streaming regime. It's in the space below n. Okay, so it's n to the 1/3, but it's for like 2 approximation of Maxcot, which again 2 is optimal. So we can prove even this type of lower bounds at this point. Okay. The open questions, well, the typical question will be, now that we can finally prove optimal lower bounds, there are a bunch of problems still that we really care about. Let's try to prove optimal lower bounds for those. There's one thing I wanted to mention. There's something nice happening with this technique. It's kind of, the graph it creates, everything it does kind of mimics the algorithmic technique that was used to design the log n pass algorithm for semi-streaming MIS. The trade-off matches it. In fact, the dynamic of these graphs that look, you do one pass and then your graph shatters into these smaller pieces is exactly what the algorithm does as well. So in some sense, we had an algorithmic technique, and then we find a lower bound that really tries to mimic that in a dual, I don't know, in a very non-formal way, it was getting a lower bound for it. And the reason I mentioned this in a follow-up work for dynamic streaming matching, we did this in the opposite direction. We first proved the lower bound for dynamic streaming matching. Then we realized, oh, we can only prove log-log. And does this mean that the algorithmic, like the dual of this algorithmic technique works there? And it turns out it works. So we managed to improve the upper bound from log n to log-log n as well. So this has been a fruitful thing that you can move between lower bound and upper bound this way. So the question will be, we also have lots of streaming algorithms that are based on iterative optimization methods, specifically multiplicative weight update. Can we come up with a lower bound techniques that tries to mimic what these algorithms are doing and to try to exploit it in a lower bound? And there are candidate problems here, for instance, 1 plus epsilon approximation of bipartite matching. The best algorithm we know is using multiplicative weight update. Can we try to come up with a lower bound techniques that mimics what the algorithm does and use it to prove a lower bound as well? And yes, that's all I wanted to say. Thank you.